Hi everyone, welcome to my YouTube channel for Kangaroo Maths and Science Academy. I believe you are all well. Our motto for the project is together we strive for a change through education. Today, guys, I want to take you through Fiscal Science, paper 2, particularly on the rate of reaction. Here it's my YouTube channel ID. Kindly follow the YouTube channel by typing at Kangaroo Maths and Science Academy. In the YouTube channel, you'll find numerous videos that I already created for maths and physical science. Kindly don't forget to like, subscribe, and hit the bell notification for future video updates. All right. Without wasting time, ladies and gentlemen, let me take you through the learning objectives. All right. The learning objectives for the rate of reactions says at the end of the session, learners must be able to define the term rate of reaction. Learners must also be able to know the factors that are actually affecting the rate of reaction. Learners must also be able to know the method of measuring rate of reaction. You must be able to make interpretations of the graphs in terms of the rate of reactions, and also in order to and also calculate the average rate of reactions based on the method of measuring rate of reaction, and also be able to explain the factors that are affecting rate of reaction by using what is called collision theory. So we are going to spend more time on this. And again, be able to use the Maxwell distribution curve in explaining the factors that are actually affecting the rate of reaction, and be able to solve problems that are relating to rate of reaction. Right, without further ado, let's now start with the learning objectives, as I just mentioned. Now, number one, I will take you through the definition of the rate of reaction. So let's just go through the definitions of the rate of reaction. Now, okay. So here I will first take you through the definitions. Okay, let me just call it number one, unit one, rate of reaction, rate of reaction. So I'll first define what is a rate of reaction. Right, there is a general definition of the rate of reaction. For now, I want to talk about it, then later we'll also come up with other definition. Right, when we are determining the rate of reaction, there is a formula, rate of reaction is equals to the changes. So this is simple for the change in concentration of, I'll just write the R/P divided by the change in time. So what does this delta here stand for? The delta here, it stands for change. So this is the change. This represents a change. And these brackets here, the closed bracket represent concentration. Concentration. Then the R or the P, the R is for the reactants, the P is for the product. Then this is just the time, change in time. Actually, let's just say change in time. Or let's just say time taken. We know that in physics or in chemistry, once we use the word rate, once we use time, if there is a time factor in our equation, then we have to use the word rate. So once you are able to understand, once you are having an equation that has to do with time, then in your definition, then you have to use the word rate. I'll give other examples. So what is the general definition of the rate of reaction? From the definition, we can define rate of reaction as the change in concentration. Change in concentration. So a rate of reaction can be defined as the change in concentration, the change in concentration of reactants. I'll just write, okay, let me just write in full. Of reactants, which is the R, or products per unit time. So the change in concentration of the reactants or product per unit time is regarded as the rate of reaction. But if we do not want to talk about change in concentration per unit time, we can use the word rate. So we can say it is the rate of change. It is the rate of change in concentration. It is the rate of change in concentration of reactants or products per unit time. Oh, no, not necessarily per unit time, because we use the word rate. I apologize. So now it means that when you are actually defining, if you are defining rate of reaction, you can either say it is the rate of change in concentration of reactants or products without even talk about per unit time. So the change is the delta, in concentration is the symbol, of reactants is the R or the P, per unit time. So we're mentioning time here. But if you don't want to use the word per unit time, if you don't want to use per unit time, you have to say rate of change in concentration of reactants or product. That is the general definition of the rate of reaction. But there's other definitions that I'm going to talk about later. Actually, this has to tell us how fast or how slow the reaction or the reactants or the product will change in terms of concentration. Now, since now we are able, remember, you can still recall this definition by doing that. Remember, I said any formula that has to do with time, you can use the word rate. For example, I apologize, but I want to show you something. Let's say you know the formula in physics, you know the formula of calculating power. This is an example. We know power is calculated by looking at work done over change in time. For example, when you are stating the law of what is this? The law of momentum, like the Newton's second law of Newton's second law in terms of momentum. The F net is equal to change in momentum over change in time. For example, acceleration, we know it's changes in velocity over changes in time. And what is another equation that has to do with time? Let me think. Okay. Then now, once you want to, if you wanted to come up with definitions like this, any equation that has to do with time, you have to use the word rate. Look at this. There is time, it's rate. There is time, it is rate. There is also time, it is rate. So let's start with this. Remember, this is change, symbol for change. This is velocity. So what is acceleration? Acceleration is the rate of change in velocity. So easy. Now let's state this. According to Newton's second law of motion in terms of momentum, it says the net force acting on an object is equal to the rate of change in momentum of that object. Right. What is power? Already with power, we cannot say is the rate of change in work done because there's no change in work done. So power will be the rate. It is the rate at which work is done. So it means any formula that has to do with time, you can use the word rate to define it. Right. So now let's move on. I hope I'm not confusing you. I wanted to address the issue of using the word rate actually. All right. And then now let's move on. So now we defined what is the rate of reaction. Now we can move on to the second learning outcome. It's very important for a learner to be able to define this. Just looking at the formula, you can be able to know that. But usually in the rate of reaction formula, they actually put a minus here. In most of the reactions, they use a minus here, which we'll talk about that later. The reason of putting a minus here is that sometimes you find that the changes in concentration or the changes in the moles of volume, it's a negative, but remember we need to avoid having the rate of friction of being negative. So we have to put this minus so that to ensure that the rate of friction is always positive. Now we'll talk more about that. Let's now proceed. Now we're able to define what is the rate of friction. Let's now move on to the next learning outcome. The second learning outcome, a learner should be able to know the factors that are affecting the rate of friction. Factors that are affecting the rate of friction. So we have addressed this one. Now we have to address this one. Let's now continue with the factors that are affecting the rate of reaction. Now let me call this number 2. Factors affecting the rate of reaction. The rate of reaction. Factors that are affecting the rate of reaction. There are 6 in number. There are actually 6 in number. Right, we have number 1. Number 1, the factor that is affecting the rate of reaction is the nature. The nature of the reacting substances. The nature of reacting substances. Secondly, we have what you call the concentration of the reactants. Concentration of the reactants. Thirdly, we have the temperature of the reacting substance. Let's just say temperature. Fourth, it is the pressure in gases. Pressure in gases. Then the next one, it is the surface area. Surface area. Or we can say the state of division. So it is the surface area or the state of division. Then the last one is a catalyst. So there are 6 factors that are actually affecting the rate of friction. However, the most important one is the concentration, temperature, pressure in gases, surface area or the state of division, and a catalyst. These are the factors that are actually affecting the rate of reaction. So it's very important for you to be able to know them. You must be able to know them. Here, when we say the nature of the reacting substance, we are referring to substances that are in solids, substances that are in gases, and substances that are in liquid. Obviously, we know that substances that are in gaseous form, they tend to react faster than liquids and solid. So solid, obvious, these are the least ones. Substances that are in gases tend to react faster than the ones that are in liquid and also that are in solid phase. But generally, the most important one, we have concentration, we have temperature, we have pressure in gases. In gases, so it means you cannot talk about pressure if you do not have the gas. We have surface area, and we have the catalyst. I want to explain this. We know that concentration is the number of moles of solute per unit solvent. So it means now we know concentration is measured by looking at the number of mole divided by volume. So we know, you see that concentration depends on the number of mole and the volume. But we'll talk more about that later. Then we also have temperature. We also have pressure in gases. We also have the surface area or the state of division. Ladies and gentlemen, these factors that I have actually explained here, they affect rate of reaction. Which means that in the examination, rate of reaction when compared with this factor, it's always a dependent variable. So it means how fast or how slow the reaction takes place depends on this factor. So which means that the rate of reaction here, it will be a dependent variable when we compare it with these factors. Remember, when one is conducting an experiment, there are three variables that we need to consider. Number one, we must have an independent variable. Secondly, we must have a dependent variable. And thirdly, one variable, other variables must be controlled. Why do we have to control variables? Usually we're controlling variable to have a fair comparison, or our experiment or our investigation not to be unbiased. We want it to be fair, actually. Right. So it means that you need to be able to understand. There's something very important that I want to allude here. Since I said these are the factors that are affecting the rate of reaction, rate of reaction or the reaction rate is a dependent variable when compared to this. What does this mean? It means if we increase the concentration of the reactants, rate of reaction will also be higher. If we increase the temperature, the rate of reaction will also increase. If we increase the pressure in gases, the rate of reaction will increase. If we increase the surface area, the rate of reaction will increase. And if we add catalyst or increase, we add a catalyst, then the rate of reaction will also increase. But there is something that I want you guys to understand, very important when you are dealing with this. You don't just talk about any of the factor. You must look at the state of phase of your substance. A substance that is in solid, you cannot talk about pressure in a substance that is in solid form. It's very, very, very important to understand. Pressure applies to substances that are in gaseous form. So you need to be able to check your state of phase of your reactants before you start deciding. which factor is actually affecting the rate of reaction. I'm repeating this. These factors are directly proportional to the rate of reaction. What does it mean? If you increase them, they will increase the rate of reaction. The higher the temperature, the reaction rate will be faster, will be higher. So it's very, very important for you to be able to understand. But usually we talk about concentration to a substance that is actually in a liquid form or in an aqueous solution. But in terms of temperature, then we can use any. But now there's something that I wanted to address, the issue of surface area or state of division. Guys, listen to me very well here. In terms of surface area, we are talking about the case that a substance in a solid form. If a substance it is in a solid phase, you can talk about surface area. But you need to understand this. Surface area increases when you take something that is in a solid form, you convert it to a powder form. Changing a substance from solid to powder, then already you have increased the surface area. Increase the surface area. So sometimes it's very important to be able to look at your reactants, check their phase, state of phase, whether they're gases, whether they're liquids, whether they're solid. You only talk about the surface area when a substance in a solid or powder form. But a substance that is in a powder form, it means you already increased the surface area of that. Let's talk about a case where we're having two pills. And these pills actually, let's talk about grandpa. Yeah, let's talk about grandpa. Let's compare two grandpa medication. One is in powder and one is in solid. And we assume they have the same mass. Their mass are actually the same. Right. If we have person A and person A and B, this one uses the one that is in a solid form. And this one uses the one that is in a powder form. With the same mass, the mass is the same. And let's say the same amount of water that they will be drinking is actually the same. Obvious, if we were to consider these two people, both of them are having headache problems. What do you think the headache will stop faster than the other? Between the one who took a powdered pill and the other one, yes, I mean to say the solid one and the one who took a powdered one. Obvious, the answer would be B. Because a substance that is in a powder form, its surface area is being increased. Or the state of division is increased, so it means the rate of reaction will be faster. But we'll talk about this, That's why in most of the courses, like if you want to do pharmacist, or maybe medicine, this is one of the chapters that one must be able to go through. That if you have a patient who's seriously ill, you need to know which medication can I give this person so that the reaction becomes faster. So you need to be able to know the rate of reaction. You need to know the factors that are actually affecting this rate of reaction. I believe you are following, ladies and gentlemen. So the factors that are affecting the rate of reaction, as I mentioned, is the nature of the reacting substances, is the concentration of the reactants, it is the temperature, it is the pressure in gases, and is the state of division on the surface area, and it's also a catalyst. We know that in terms of a catalyst is a substance that speed up or increase the rate of reaction without undergoing any permanent change, but actually it by lowering the activation energy. We'll talk about this. That's why we'll be talking about some of the factors in the second chapter, which is for chemical equilibrium, that affect chemical equilibrium, except within these 6 of them, there are only 3 that are affecting chemical equilibrium, which we'll talk about. And I will explain why are we saying the only one that are affecting chemical equilibrium. I believe you're following. So now, I want us to move on to the next learning outcome, which we call it number 3. Let's call it learning outcome number 3. In the learning outcome 3, one must be able to know, if I'm not mistaken, the methods that we can use to measure the rate of reaction. Guys, I think this is very, very, very important. Let me explain the method of measuring rate of reactions. Okay, methods of measuring rate of reaction. There are 3 methods that can be used to measure the rate of reaction. Number 1, rate of reaction can be measured by looking at the changes in volume. The changes in volume of the products. Let me just say changes in volume of produced gas. The changes in volume produced. Changes in volume produced. So it means in the product produced. Come on. So we can look at the changes in volume produced. Okay, so we can look at the volume of the gas produced. What do you mean by this? It means if we, let's say during an experiment, we conduct the following. So let's say we take a conical flask. Okay. So if, let's say we have a conical flask. Okay. I hope you can see it. Okay, fine. So this is our conical flask. I'll just call it a conical flask. Okay. Then within this conical flask, maybe we add two substances or the reactants. Then within this, we actually conduct the following instruments. Okay, let me just use, it's fine. So I wanted to, okay, let's call this a conical flask. Conical flask. Then in this conical flask, we actually put a stopper. Let's say this is our stopper. Okay. Okay, here it's our stopper. Within this stopper, we put what we call a delivering tube. Sorry, that will go inside here. So this delivering tube is connected to the gas syringe. I believe you know what is a gas syringe. Okay, let's say we have something like this with values there. Okay, something like this. All right, then within this conical flask, okay, apologize. Then we have the okay, let's call this is the gas syringe. Actually, the function of a gas syringe is to measure the volume of the gases produced. To measure volume of gas. Okay, volume of gas produced. I apologize, guys. So we can use it to measure the volume of the gas produced. Okay, can use the gas syringe to measure the volume of the gas that is being produced. Okay, let me raise this. Right. So gas syringe, we can use this to measure the volume of gas produced. Measure volume of gas produced. Now, this is actually a delivering tube. Delivery tube. Let's just call it a delivery tube. Then this is a stopper. This is a stopper. It's there like to allow the gas just to be released inside the tube only. So this is our stopper. Okay. Now, remember, wherever we use a gas syringe, it shows that the method that we are using here to measure the rate of reaction, we use changes in volume produced. Changes in the volume of gas. Let me just say changes in the volume of gas produced. I apologize, guys. Changes in volume of gas. Changes in volume of gas produced. So it's very important for one to be able to know this. Changes in volume of a gas produced. I'm still repeating the same thing. Okay, it's fine. Yeah, let's do this. Changes in volume of gas produced. So now, what does it means? Inside there will be will having the reactants. or the reacting substances here. So these reactants, when they react, we'll be looking at how fast actually the volume of the gas that is being produced, looking at time, in terms of time, we'll be recording that. So you will realize that if we do this algebraically, I'm not saying but graphically in terms of the information that we're going to get. Here it means we'll be looking at time, the time and the volume of the gas. So on the y-axis, I'll talk about the volume of gas, usually let's say in centimeter cubic or in decimeter cubic. Then here we're looking at time in seconds. Already at the start of the reaction, the time is 0. The volume of the gas that was produced is also 0 because we're talking about the product. But when time increases, the volume of the gas actually increases up until the rate becomes smaller. So end up, we're going to have something like this. So graphically, if we draw a line here, let's join the points here. Okay, let me use, let me use this one. So you realize that the graph will look like this. So if the graph looks like this, okay, just a minute, let me correct something here. Just want to correct something. Right. Okay, so we're going to have something like this, ladies and gentlemen. So the point will just be, let's say it's there, and then the one is there. Okay, I want to talk about this. So now if we reconstruct this, the graph will look like this, okay? Okay. Okay. Yeah, we have something like this. You will realize that, remember, we are talking about the volume of the gas that is being produced. At time 0, the volume of the gas produced was 0. But when time increases, the volume of the gas increases up until it becomes constant after some time. Let's just say in terms of the time here, let's say within this period here, let's call it T1. Let's say somewhere here, let's call it T0. Then this is going to be, okay. Then you'll realize that the reaction is the fastest at the start, especially at this point here. But when time increases, the reaction or the gradient, let me talk about the gradient becomes gentle. Somewhere here, if you look at this, just between anything below 0 to T0, the graph is actually steeper in terms of gradient. But after T1, the graph is now gentle. And these are exam questions, like you need to be able to know that, okay, fine. What could be the reason of this graph becoming gentle after T1? Remember, after T1, the volume is now the same. The volume produced is now the same. It's actually constant, actually. So what does this mean? It means that the reaction has stopped after T1. This is an indication that the reaction has actually stopped after T1. So there are possible reasons. We can say the reaction comes to a completion, or actually, let's just say actually come to completion when it's somewhere here. But let's just say the reaction stopped. The reaction ended or the reaction stopped. This is an indication that the reaction stopped. The reaction stopped. Or we can say the limiting reactant, this is another reason. Limiting reactant is used up completely. Now, completely. The question is, when we are dealing with the rate of reaction, ladies and gentlemen, how do we, when we are using the method of measuring rate of reaction by using, volume of gas produced, how can we measure the rate of reaction here? To measure the rate of reaction when we are given a graph, we are actually determining the gradient . As I was saying, that we can calculate the gradient between the volume of gas produced and the time. And remember, on the volume of the volume is this the y-axis and this is the x-axis. So let's now determine the gradient. Now, in determining the gradient, we'll say change in y over changes in x. So the change in y will be the changes in the volume, the changes in volume, and the x will be the change in time. So we're going to have change in v over change in t. So the volume, we know, we're looking at the changes in volume, which is in centimeter cubic according to the unit, to the units I said. The time is in seconds. And this, it's actually called the average rate of reaction. So we can determine the rate of reaction or the average rate of reaction by looking at by determining the gradient of the volume against time graph. So which means that this is another method that we can use to determine the average gradient on a curve. So it means one can define rate of reaction if you are given rate of reaction as the change in volume instead of concentration. Change in volume of gas. Volume of gas produced per unit time. So this is another definition for the rate of change. So we can say it's the rate of change in volume of a gas per unit, the rate of change in volume of a gas. I apologize. Now, as I was saying, look at this. It shows that as the start of the reaction, actually the graph is faster actually here. This is the fastest actually here at the start of the reaction. But when the reaction start to at the highest, it shows that now the reaction is very slower. Then it's now coming to a completion, then it's now gentle. So it means when the graph is gentle, it shows that there's a zero reaction rate. And there is a zero reaction rate. The reaction rate is 0 because the changes in volume is 0, even though there's a change in time. Because of that, then we're going to have a 0 reaction rate. So this will give us a 0 reaction rate. So you must be able to know in the exam and to be able to tell, like, to be able to know how to calculate the rate of reaction. So it depends with the unit. Sometimes the time can be in seconds, can be minutes. So it depends with the scenario. Now, another question would be, what if we have two graphs? What if we have two graphs and we wanted to check which one on average was faster than the other? We need to actually check which of the graph on average is faster than the other. Okay, let's do this. Let's say we have another graph. Okay, let's call this, okay, that's fine. Let's say we have a point there, then we have another point. Yeah, I'm gonna draw another graph just to explain the relationship between these two graphs in terms of the reaction rate. Okay, I apologize. I want them to be gentle here. Okay, let's call the first one, let's call the second one to be the B, and the first one to be A. Let's call this one to be the reaction A, and this one to be reaction B. You will realize something, that in terms of this graph, from the start of the reaction, the gradient of reaction A, it's actually bigger than the gradient of reaction B. Why am I saying this? Look, if we were to measure the volume, let's say we were told to estimate the volume of the gas produced for B and A at time 0. Yeah. You'll realize that at time 0, the volume of gas B will be somewhere here. And at the same time, the volume of gas A will be there. You see that at the same time, gas A produces more volume than gas B. Which means, let's assume, let's say the volume here is 40 and the volume there is 80. And the time at T0, let's say it's around, let's say 5 seconds. We want to calculate the average rate of friction from 0. Obvious, when you compare this, let's try to do it here. So I will say I want to compare the rate of reaction for A and also the rate of reaction for B. Remember, we said is the change in volume over the change in time. Change in volume, we are referring to the final volume minus the initial volume divided by change in time. Let's start with A. What is the final volume? Remember, we are comparing up until T0 here. It means this is the final, so we want these changes here. So this will be 40. No, for A, not for B. Because the one I'm talking about there is for A. For B, for B, it will be 40 minus 0 with reference to 0. Divide by the time, it's 5 minus 0, 5 seconds minus 0. Let's come here, 80 minus 0 divided by 5. We want to compare the rate of reaction. So the 80 minus 0, which is 80, 80 divided by 5, this will give us 16 centimeter cubic per second. And this one will give us, oh, it's 40, I apologize. 40 divided by 5, it will give us 8 centimeter cubic. So which one, in terms of the gradient, it's higher than the other? Obvious, A has higher gradient than B. You see that in terms of this reaction A reacted faster than B. What could be the possible reason? Because of the gradient. The steeper the gradient, the higher the reaction rate. Steeper gradients, steeper the gradient, or steeper the graph, actually, the steeper the graph it is, the steeper the graph, the faster the reaction. The faster the reaction. So you need to be able to tell which graph is actually faster than the other by looking at the gradient. And you can be able to know which graph reacted faster than the other. So it's very important to know that, okay, looking at this experiment A reacted faster than B because its gradient is steeper than that of B. But after T1, they both had a zero rate of reaction. It means they come to a completion or they came to a halt. So it means if usually when we say calculate the average rate, it means you must compare it from where the reaction has become gentle. From like usually if they were not told to calculate it within certain intervals. So this is the first method of measuring rate of reaction. I think I explained it. So we can measure rate of reaction by looking at the changes in volume of the gas produced. And usually you'll see by the gas syringe here, we are looking at the volume of the gas produced. But not necessarily that, but in most of the cases, if there's in the product, if there's a gas that is being formed, then we can also use this method will be applicable. Secondly, let's move on to the next part. The second method of measuring rate of reaction is to look at the changes in mass. We can look at the changes in mass of the reactants. We can look at the changes in mass of the reactants. How fast or how slow the mass are actually changing. Right. Now, number 2, let me call it 3.2. The second method will be change in mass. Change in mass of the reactants. But usually this one is applicable when one of the reactants it is in a solid phase. So we can look at the change in mass of the reactants. Now, actually, usually with the change in mass, it means we can bring along a beam balance. That is the instrument that we use to weigh substance. It's our beam balance, maybe with numbers on it. So what you can do, let's say we put a conical flask on the beam balance. Okay, I'm not good in drawing. Okay, fine. Right, here it's our conical flask. Inside this conical flask, maybe we put, let's say, substance like magnesium. No. Okay, let me just say magnesium because it is a solid. Let's say this is our magnesium inside here. Okay. Then right. In terms of that, let's call this magnesium. So is the magnesium Mg. It's a solid. Then inside this, we also use hydrochloric acid inside as a solution, HCl as an aqua. Obviously, this reaction has to take place. Then we'll be measuring, initially we'll measure the mass of magnesium before adding this acid. And after some time, we want to check how fast or how slow is the magnesium decreasing in terms of mass. So it means the method that we're going to use here is the changes in mass of the reactant. But in terms of this, we know that if you take magnesium, just an example, as a solid, you combine it with hydrochloric acid. This will actually give us, if we are using MG, okay, it will give us magnesium chloride and hydrogen gas. You see here, we have a gas. There is a gas that is being formed. So it means we can still use the volume of gas produced to measure the rate of reaction. But here, I'm talking about the mass, the changes in mass of this magnesium. So now it means now we'll be recording, comparing the changes in mass against time. So graphically, it means we will be having something like this. So now we'll be having something like this. So it means on the y-axis, we'll be having mass, the mass of a substance in grams. Then here we're comparing this against time. Obvious, at time 0, the mass of magnesium will still be at its maximum, somewhere here. Because remember at time 0, like when we measure, like when we recorded the mass of magnesium, it will still be at the maximum. But when times increases, the mass of magnesium decrease, maybe becomes 0 or yeah, after some time, then we have something like this. So now you see that if we construct a graph here, I mean, we join the points here, the graph will look like this. Then this is another method that we can use to measure the rate of friction by looking at the changes in mass. Remember, at time 0, somewhere here, it means the reaction is still the fastest here. But when reaction increases, the mass starts to decrease up until the graph becomes gentle. So which means that the reaction has stopped, or reaction has come to a halt. So we can still determine the average rate of reaction, or measure the rate of reaction by looking at the gradient, as I said earlier. But we can calculate the gradient of this function. We know that gradient is the change in y over change in x. So this will be the change in mass over the change in time, because remember I said change in y over change in x. So which means if you look at remember the mass is in gram, the time for now it's in seconds. So this is the rate of reaction. It's the average rate of reaction. So we can determine the rate of reaction by looking at the changes in mass over the changes in time. So which means we can measure these in grams per second. So you see that it's another method that we can use to measure the rate of reaction. So it means in the exam, we can still define rate of reaction as the rate of change in mass, the rate of change in mass of the reactants, particularly the one that is in solid. Or we can say the change in mass, but usually the general one, we know the general definition of the rate of reaction. So this is another way of determining the rate of reaction. But honestly speaking, in the exam, they usually ask about this change in mass or the changes in volume. I believe you are following. Right. Let's move on to the other method of measuring the rate of reaction. I want us to move on to other method of measuring the rate of reaction. Okay. Now, let me erase some of, because already we defined what is the rate of friction. And yeah, let me just create a space here so that we start with other things. I believe you are following. Kindly don't forget to subscribe and like and hit the bell button for future video notifications. I believe you are enjoying the session. Okay, now I'm gonna talk about the last method of measuring the rate of reaction. But this one usually in the exam, they just use it in some cases, but yeah, usually if they want to ask you to determine the rate of friction, yeah. But the most important ones are the first two. But we also have to know this one that I'm going to talk about now. Okay, let's continue. Just a minute. Okay, let me use this. Okay. So number 3.3, we can measure the rate of friction by looking at the color change. And this color change can be used like in two ways, whether when we're looking at what we call a precipitate formation. And guys, what do you mean by a precipitate? A precipitate is just a solid substance formed in a reaction or produced in a reaction. A solid substance that is actually formed in a reaction. It's called a precipitate. Or we can look at the color change if you have an indicators, if you're using indicators. Now, let's look at this. Usually in the exam, this process of color change is to do with what we call turbidity. So now, in the process of color change, they usually do this during an experiment. They use a process called disappearing method. They use a process called disappearing method. So it means it has to do with observing actually. What they do is maybe they just use a beaker or a conical flask. Yeah, any glass beaker. Let's say, yeah, we can just use the conical flask. Okay, let's say they use conical flask. I'm not good in drawing. They actually do this. Under this conical flask, they put like a paper. And within this paper, they mark it. They put a cross on it. Actually, they can make a cross here. Then now, within this, someone has to observe inside there. You need to observe here. Like whatever the solution, they try to mix this. They look at the solution before reaction. When they observe here, they have to see this mark here. But now, when times changes, they will be recording time actually. When time changes, they now have to, okay, I apologize. They now have to look at like how fast or how slow is the color or the mark is actually disappearing in terms of color changes. Remember, you are actually like when you're conducting this, you just observe inside this while looking at the mark. before reaction already, let's say inside here we just had hydrochloric acid, or we had magnesium. Then like we do what? We mix this with magnesium. This is an example. Then now we start looking at the color change of this. Like, no, like how fast or how slow is this mark disappearing? Obvious, when times increases, or when the reaction proceeds, we want to know how fast or how slow is this color actually starting to disappear. Like when we are looking this side, is it visible? Are we still able to see the color? And how fast or how slow is this taking place in terms of what? Let's say when times continues, you find that there's a product or there's a gas that is actually being formed here. Obviously, when there's a gas that is being formed, when you look this side, you no longer be able to see the color. The color will start to disappear. I'm saying the mark, I mean to say the mark will start to do what? To disappear. So this actually referred to color change. For example, let's say the color, the reactants maybe were red in color. Then suddenly the reactants are now they're now yellowish. It's just an example. So this is another method that we can do to measure the rate of reaction. But this time around, since we are not actually measuring the color, we are actually recording the time. So it means here, the only way we cannot plot the graph against the color, we can only determine the rate of reaction by doing this. Rate of reaction. With this, we can look at one color change. Okay, let's say we consider one color change over the changes in time. So it means the formula for calculating the rate of reaction when we are dealing with color change is just 1 over the change in time. Because right, it means like we are just recording, like we want to check how fast or how slow is this color actually changing to yellow. Maybe we can record it for the first time, then we check it for the second time, then we look at the changes in that. So this is the method of determining the rate of reaction by looking at the color change. But this time around, we use 1 over time. So it means if the time is second, to just be 1 over second. Unlike when we are using, what is this? The mass of the changes in mass of the reactants, or the what is this? The changes in volume. Very important, ladies and gentlemen. I believe you are following. I think I will explain by using the examples. Yeah, so it's 3 things. Is the color change, it is the changes in mass of the reactants, or it is the change in volume of the gas produced. So 3 method. But like graphically, if you want to plot graph, the only way is to use changes in mass or the changes in the volume of gas that is being produced. I believe you are following, guys. I strongly believe you are following. So we spoke about the factors that are actually affecting the rate of reactions. Then, yeah, let's continue. Okay, thirdly, we need to be able to, like the issue of interpreting graphs. I think I have addressed that one, that you need to look at the gradient of the graphs. The steeper the gradient, the faster the reaction. But as the gradient starts becoming gentle, or as the graph is becoming gentle, then it shows that the rate of reaction is becoming 0. The rate of reaction is 0. So it's very important to be able to identify that. Okay? Yeah. Just a minute. I think there's a network issue this side. Okay, now let's continue. Now we have addressed the method of measuring rate of reactions. And now we made interpretation of the graphs in terms of rate of reaction and how to calculate the average rate of reaction. Remember I said I calculate the average rate of reaction by looking at the gradient. On method of measuring rate of reaction, I think we spoke about this. But when we look at changes in volume over changes in time, is still the average rate of reaction. Changes in mass over change in time is still the average rate of reaction. But 1 over change in time is when we're dealing with color change. So it means now we can move on to explaining the factors that are affecting the rate of reaction by using collision theory. Okay, let's talk about collision theory. Okay, let's talk about the collision theory. Collision theory. Okay, according to this theory, the theory states that in a reaction, for the reaction to take place, or for the chemical reaction to take place, the theory suggests that the reacting substances should collide, or the reacting particles should collide or must collide with sufficient kinetic energy and correct orientation. That is according to collision theory. The collision theory says that for the reaction to start or for the reaction to take place, particles must collide with sufficient kinetic energy or enough energy or kinetic energy. Let's just say sufficient energy or enough energy. Whether we use sufficient or use the word enough. Enough energy actually, and correct orientation. That is what the theory states. It states for the reaction to take place, the reaction must have reacting particles, and these particles must collide with enough energy, and also they must have a correct orientation. What does it mean? Now, this takes us to a part called Maxwell distribution curve. I want to explain this so that you understand. According to this, it says, if a reaction is taking place, the reacting substances must have particles that are actually colliding with sufficient energy and correct orientation. Sufficient energy and correct orientation. What does it mean by this called sufficient energy? We know very well that for the reaction to start, it needs an energy, and this energy is called an activation energy. Which in other book we call it the EA. So we know the activation energy is the minimum energy needed, the minimum amount of energy that is needed for the what? For the reaction to start or for the reaction to begin. So this minimum amount of energy that is needed for the reaction to start is called the activation energy. And what does it mean by what we call sufficient kinetic? Actually, let's use the word sufficient energy. Obvious, when we talk about an energy that is actually sufficient, it should be an energy that is actually bigger or equal to the one that is needed for the reaction to start. So it means we are saying, when we say we have sufficient energy or kinetic energy, it's when the kinetic energy or the average, let me just say the average kinetic energy, it's when it's bigger or it's equal to the activation energy, the energy that is needed for the reaction to start. Then this is called sufficient energy or kinetic energy. Sufficient energy or enough energy. I apologize. So if we say the reaction must collide with sufficient energy or sufficient kinetic energy, let's just call it energy. So it means the average kinetic energy should be greater or equals to the activation energy. We know in physics paper one that when you talk about kinetic energy, we're talking about the energy due to the motion of an object. Remember, we're talking about particles that are actually colliding. So you see that when the particles start to collide, they now are exposed to what you call the kinetic energy due to the movement. So the average kinetic energy in that particles, if it's higher or it's equal to the activation energy, then it means then now the reaction is actually beginning, the reaction is taking place. Remember, the minimum energy that is needed for the reaction to start is the activation energy. So what does it mean? It means that the reactions that have energy that is less than the activation energy will not take place, because this is the minimum amount of energy that is needed for the reaction to start. So if we say, according to collision theory, it says particles must collide with enough energy, which means they must collide with energy that is actually bigger or equals to the activation energy, then the reaction will take place. Actually, it will take place faster. So what does this mean? It means that since we know that for the reaction to take place, or for the chemical reaction to occur, particles have to collide with sufficient kinetic energy. And I explain what we mean by sufficient energy. All right. Now let me talk about this incorporating what is called Maxwell distribution curve. According to the Maxwell distribution curve, let me just okay. What can I do? Okay, fine. Because I wanted to have enough space here. Okay, let me do this. Okay. According to the Maxwell distribution curve, here we are comparing the number of particles and the energy involved, or actually we can say the kinetic energy involved. So I'm gonna draw a graph here and explain it thoroughly. So let's say we have a graph here. This is the graph, the Maxwell distribution curve. And it's very important to know this curve. Right. On the y-axis, we're gonna put the number of particles, number of the reacting particles. Let's just say number of molecules or number of particles. On the x-axis, we talk about the energy or the kinetic energy. Now, already at the start of the reaction, this is the point where the kinetic energy is actually zero. But after some time, it increases and reaches maximum, then now it decreases. So we're going to have something like this. Let me just try to reduce it. Yeah, just want to, but it's too fine. There's no problem. Let me just, right. I want to explain this. Now, let's call this point. There's a point. Let me make this point here, this point. And it's very important to be able to know this. This point here. This point, it is called the activation energy, the EA, the activation energy. You need to listen to me very well so that you can be able to understand. Which means if we have an activation energy, any energy that is below the activation energy, any kinetic energy that is below it means it's where we have is this side, it's where we have this side, it's where we have EK, or let me just average EK, but it's fine. Let me just say EK, it's less than the EA. The kinetic energy is less than, so every kinetic energy is now below the activation. And we know that for the reaction to begin, this activation energy is actually required. So it means any reactants that have have a kinetic energy or an average kinetic energy that is below the activation energy, it means they do not have sufficient kinetic energy. So it means this region here, let me use a different color. This area, it is the area where the activation energy, it's less than, I mean, the average kinetic energy, it's less than the activation energy. But how about this part, this other part, this side? Obvious, this side, this area, this region here, it is an area where if we were to calculate average kinetic energies here, it is an area where the average, let me use black. This is an area where if we calculate the average EKs, on average, the kinetic energy is greater or is equal to the activation energy, this one here. And we know that when the kinetic energy is above the activation energy, it means the particles here have sufficient energy or have enough energy to collide. So this is the area where particles have enough sufficient, enough or sufficient, okay, enough or sufficient energy. When we say enough or sufficient, it means their kinetic energy on average is greater or is equal to the activation energy. This is bigger than what is needed for the reaction to start. It shows that the reaction will become faster. But if the activation energy, the kinetic energy is less than, it means this side, it's where particles have no sufficient energy. Now, it means that you need to consider the region that is above the activation energy. So now, let's take this further. So it means the higher the area of where the activation energy, like kinetic energy is bigger than, so the higher the area, it implies that the reaction will be faster. Particles with enough kinetic energy, with enough, yes, enough energy or enough kinetic energy, because the kinetic energy on average is higher, is greater or equals to the activation energy. So what does this mean? It means we can take this further and say, okay, fine. What are the factors that can actually, how can we use this collision theory to explain the factors that are affecting reaction rate? Number one, according to collision theory, it says for the chemical reaction to occur, particles must collide with sufficient energy or with enough energy and correct orientation. So it means that if particles are colliding with enough sufficient energy and correct orientation, they will result to more particles. More particles will collide per unit time. And if more particles are colliding per unit time, the number of effective collision also takes into account. So for now, let's just forget about more or being less. So we're going to talk about the number of particles that are colliding per unit time. So these are actually the factors that are actually affecting the rate of friction. Let me, instead of saying more or less, let me say the number of effective collision. No, I'm saying number of particles, the number of particles colliding per unit time. Number of particles colliding per unit time. Number of particles colliding per unit time. And the number of effective collision. Number of effective collision per unit time has an impact towards the rate of friction. So it means if the number of particles colliding per unit time are more, then it means then the effective collision per unit time will still be more. And once we have more effective collision per unit time, it means the reaction rate will be faster. Faster reaction rate. But if the number of collisions, the number of particles that are colliding per unit time are less, then it means the effective collision per unit time will still be less. Then the reaction rate will be slower. Now, what if now we have another graph? Let's say we have another graph. We wanted to know between the two, let's call this A. Between these two and this other one, which one will react faster than the other? Obvious. Let's do this. Let me add another graph here. Okay, let's say we have another graph here. This is the start. It's just an example. Let's call this B. Right. What is very important, we need to consider where the kinetic energy is bigger than the activation energy, which means this point here. Now, but let's do this. Let's now shade the area of this B. We're actually concerned where we have sufficient energy, because we said for the reaction to begin, the reacting substance must have sufficient kinetic energy and correct orientation. What does this mean? It means that within this, the two graph A and B, both of them, they have sufficient energy. But now look at this. Let us now look at the number of particles. If you look at the first one, like the graph A, this one, we're actually concerned about when they're above. Look at the area. The area for graph A, this is the area where particles have sufficient energy. Particles with sufficient energy. But if we had to compare this area and that one for B, you'll see that the area for B is actually higher than that of A, which means for B, more particles have sufficient energy and correct orientation as compared to that of A. And remember, if more particles have sufficient energy, it means what? Number of particles that are colliding will be more. And the effective collision per unit time will be more. It means the rate of friction will be faster. It means reaction B reacted faster than reaction A. We look at the area where the activation kinetic energy is above. The higher the area, the faster the reaction. You need to know this, and this is very important when you're using Maxwell distribution curve. Now, let me try to split them so that you can be able to understand. So now I've incorporated the collision theory and Maxwell distribution curve. So if more particles that are colliding or more particles are having sufficient energy, which is the average kinetic energy that is above the activation or equals to, then it means more particles will collide per unit time. And if more particles are colliding per unit time, it means the number of effective collisions will be more. And once we have more effective collisions per unit time, then the reaction will be faster. Let's look at this. This is the activation energy, EA. So it means this is the part where the average EK is greater or equals to EA. Okay? Now let us draw another one. With the same activation energy. But this time around we have this. Okay? You see that the EA is still there, which means this region, this area, that's where we have the average EK is greater or equals to EA. So it means that's where we have enough kinetic energy. Yeah, enough kinetic energy. Particles with enough kinetic. But look at the area. The area here, it's smaller than that of, which means less particles here have enough kinetic energy. But here, more particles have enough kinetic energy. So it means as a result, the number of effective collision this side will be more than that. And because of that, it means this direction will be faster than that of than this one. So it means when you are talking about the factors, you have to talk about the number of particles that are colliding and also the effective collision per unit time. Then you decide whether the reaction is faster or slower. I believe you guys are following. This is called Maxwell distribution curve. That's why in the effect of a catalyst, remember a catalyst do what? Speed up the reaction by actually lowering the activation energy. It reduces the activation energy. If we were to draw the potential energy graph, let's say this for endo, then we add the catalyst. We know the catalyst does not change the reactants and the product. It's just there to do what? To speed up. You see that the activation energy has been reduced because from here up until the activated complex, this is the activation energy. But now the activation energy is being smaller now. So you see, if we add the catalyst among this, look what will happen. Adding a catalyst here will actually reduce the activation energy. If the activation energy was around 40 kilojoules, now it will be less than. So it means the activation energy is now here. It's here. And by so doing, it means since the activation energy is here, it's now creating an area. It means it's creating this area. You see this area now. Okay, let me use the same color. Remember, this is where we had particles that are having with enough kinetic energy. Now, it shows that the particles are now increasing. So more particles now are having what? Sufficient kinetic energy. You see, this area is now increasing. You see now the area is increased. So it shows that more and more particles are now having enough. Because of that means direction will now be faster. Because the area now is being increased. The area where, remember, this was the part where, this was the part where particles were not having enough kinetic energy. Now they're having, because of we reduce the activation energy. So it means if we keep on reducing, it means more particles will now start to do what? To have sufficient kinetic energy. So I strongly believe you understand that. And these are exam typical questions, ladies and gentlemen. So it's very important to be able to know or to be able to interpret this in terms of collision theory. All right, I want us to take this further and we look at the questions. I want us to look at the questions. Okay. Oh, I stopped the sharing. Okay. All right, let me share again. So now let's go through this. I just want to check what we've covered already. We went through rate of friction, we defined it, we look at the factors, method of measuring, interpretation of the graphs, factors that are affecting collision theory. We'll look that in the example, in the examples. We also explain Maxwell distribution curve to explain the factors that are affecting. Then now we must move on to problem solving. I believe you guys are following. Okay. Let us now move on to into the questions. Okay. 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 Okay, guys, I think my machine is about to die now. What I'll do, let me try to summarize this, then I'll create part 2 of the video. All right. In terms of what we said, we define what is the rate of friction. We said rate of friction, it is the change in concentration of the reactants or product per unit time, or you can define it as the rate of change in concentration of the reactants or product. We looked at the factors that are affecting the rate of friction. The first one we said we have the nature of the reacting substances. Secondly, we spoke about the concentration of the reactants. We spoke about the temperature. We spoke about the pressure in gases. We spoke about the surface area or the state of division. We also mentioned about the catalyst, or yes, the catalyst, which we actually call it a positive catalyst. Then again, we went through we went through the, okay, just a minute, guys, I want to, we also went through the method of measuring rate of reaction, where we said we can measure the rate of reaction at looking at the volume of the gas produced, and also we can also look at the change of the change in volume of gas produced, and also the change in mass of the reacting substance. And also we can look at the color change, usually by looking at the precipitate formation or the indicator, by looking at the indicators in terms of color changing. Then also we have looked at how like to interpret graphs, checking in which reaction is faster than the other in terms of gradients. The steeper the gradient, the faster the steeper the graph, the faster the reaction. And again, we looked on how to calculate the average rate of reactions. In the changes, in looking at the changes in volume, we look at the changes in volume over change in time, which we can define as the rate of change in volume. We can also look at the change in mass. We also explained the factors that are affecting, like I just explained collision theory, that a collision theory is a theory that suggests that for the chemical reaction to occur, particles must collide with sufficient energy or enough energy and correct orientation. And we went through what we mean by enough or sufficient energy. Sufficient energy is where the average kinetic energy is either greater or equals to the activation energy. Then we know that if particles more particles are colliding per unit time, it means those more particles will have more particles are colliding with sufficient energy and correct orientation. It means you'll have more effective collision per unit time. The reaction will be faster. And we also went through the Maxwell distribution curve. The higher the area where the activation energy is bigger than the kinetic energy is bigger than the activation energy, then the faster the reaction. So we look at the area. This is where the activation is bigger. The activation energy is greater than the EA. But if we were to have something like this, with the same we look at the area. It means more particles here, more particles have sufficient energy. So, and if more particles have sufficient energy, it means the reaction will be faster in this than in that one. So I believe you guys are following. Let's continue with the problem solving for the rate of reaction. As I said that through the summary that I have just explained, now we are going to solve problems, right? We'll start with tutorial number 1, which is from June 2021 senior certificate question paper. Right. In terms of this one, this is question 5. It says that 2 experiments 1 and 2 are conducted to investigate one of the factors that affect the rate of reaction of aluminum carbonate with excess hydrochloric acid. So we are told that here they want to investigate one of the factors that actually affect the rate of reaction of aluminum carbonate with excess hydrochloric acid. So we are told that hydrochloric acid is in excess. So what does it mean? It means its initial mole, some of its mole has reacted and some of its mole will remain in the reaction. So it is the unreacted. So it means not all of its mole will be used completely, others will remain. And if they are saying hydrochloric acid is in excess, it means Whatever it is reacting with, it will be regarded as the limiting reactant. It will be a substance that will be used up completely in a reaction. Now, we know that we want to investigate one of the factors that affect the rate of reaction. We know that factors that are affecting rate of reaction, the first one is concentration, followed by temperature, followed by pressure in gases, followed by state of division or surface area. Then lastly is the issue of a catalyst. But let us now look at the reactants. They are reacting aluminum carbonate, which is a solid, with hydrochloric acid, which is an aqua. So which means when you look at this, pressure will not be part of, will not be a factor that we want to investigate. I mean, if we were to, just on my assumption. Why? Because we are not dealing with gas. So since there is no gas involved, means we're not going to talk about pressure here. Before I look at the questions. And again, with aluminum carbonate, we can speak of temperature, we can speak of a catalyst, and we can speak of surface area. I mean, in terms of the investigation. But let's just go through this. There is something that I need to explain here. They told us that this hydrochloric acid was in excess. So if hydrochloric acid is in excess, it means whatever is reacting with it will be used up completely. So this will be the limiting reactant. It means not all of the moles of substance of hydrochloric acid will be used up, or all of it. Some will remain in the reaction. Now let's also look at the product. The product is aluminum chloride with water and tetrachloride. Yes, with water and carbon dioxide. Carbon dioxide is a gas, so which means we can be able to tell the method that was used here to the method of measuring rate of reaction. It might be the mass, the changes in mass of the volume of gas, but let's just go through it. The apparatus is used is shown below. If you look at the apparatus, one of the apparatus here, this is a gas syringe. And we know that the function of the gas syringe is to measure the volume of a gas. So already we can easily tell that the method that they've used here to measure the rate of reaction is the changes in volume of gas produced. Then we have a conical flask, we have a delivery tube, there's a stopper, and there's also a tube for the acid. It means like here they've inserted the acid. This one is for a base. No, not necessarily base, but it is aluminum carbonate. They have to react, but the hydrochloric acid, we are told that is in excess. Right, the reaction condition used for the experiment are as follows. Let's go through the reaction conditions. According to the reaction conditions here, we are comparing to experiment 1 and experiment 2. The first experiment, it says that 100 centimeter cubic, which is a volume of 1.5 mole per decimeter cubic. So this is a concentration of the acid. It reacts with 0.016 mole of aluminum carbonate, granule. So they spoke about granule at 25 degrees Celsius. Also, this side is also granule at 25 degrees Celsius. So you can easily see that here, the surface area of aluminum carbonate is controlled because they're both solid, they're both granule. And also the temperature is controlled. So if you wanted to talk about the controlled variable here, we'll talk about surface area and temperature that control. So what are we actually investigating here? Because already pressure is not part of state of division is controlled because they're both granule. Temperature is also controlled because both are at 25 degrees Celsius. So what are we actually investigating here? What we're investigating is what is actually changing between the two, which is the concentration. Hydrochloric acid has different concentration. So I want to compare these two experiments with respect to concentration. So it means if we were to talk about the independent variable, the dependent variable is what we're actually looking at. Yet it will be the rate of reaction. Then the independent here, looking at this, will be the concentration, the one that is changing. Okay, I apologize, guys. Just had connection issues. Apology for that. All right, let's now continue. Okay, as I was saying, okay, let me just use a permanent marker, like the word tool here, so that I must not keep on erasing. Okay. So looking on this, you can easily see that as I said, that one is in excess and one is the limiting. Then now we can just continue. Let me just use the red one. So what I was actually saying that we have an independent variable, dependent and controlled variable. Already there are two variables that are actually controlled. It is the temperature, because the temperature of the both experiments are at 25 degrees Celsius. And it's also the surface area. Surface area. One can also mention about the number of mole of aluminium carbonate. So now, what is an independent? Independent here is the concentration. I know it's not part of the question, but I'm just answering it. Then the dependent is the rate of reaction. So this is the limiting, as I said. This is an excess. Okay. Right. Then now, the reason I said concentration is an independent variable is what we're actually investigating, because it's changing here. And you can easily see that experiment 2 has higher concentration than experiment 1. And we know that the higher the concentration, actually, the faster the reaction. Now, let's now proceed. The first question says, define the term rate of reaction or reaction rate. I think I spoke about that. That the rate of reaction is the change in concentration of reactants or product per unit time, or is the rate of change in concentration of the reactants or product, or you can say is the change in volume of gas produced per unit time. You can talk about the issue of changes in mass. There's no problem with that. Right. Then now let's look at like the relevant one will be the change in volume of gas produced, because here we are measuring the method that we're using to measure rate of friction is the changes in the volume of gas produced. So already we have answered the first one. We can now proceed. Okay. So now we can now proceed. I believe there's no need for me to write this up again, but let me just write it in full. Is the change in concentration of reactants or products per unit time. Okay. Then secondly, using the experimental setup above, state the measurement that must be made to determine the rate of this reaction. So actually we need to tell about the method that was used to measure the rate of reaction here. Obvious, here we're going to look at the volume of gas produced, or the changes of volume of gas produced, volume of gas produced. The volume of gas produced. So this is the method that was used here. State the measurements that must be made to determine the rate using the experimental, or state the measurements that must be used. It means here, by measuring the volume of gas produced, we need to use the gas syringe, which is used to measure the volume of the gas produced. So it means, yeah, the gas syringe will be used to measure the volume of the gas that is produced here. Right. Then use collision theory to explain how the average reaction rate in experiment 2 will differ from the average reaction rate in experiment 1. We need to use collision theory. So what does this mean? It means we're going to compare experiment 1 with experiment 2. So we're going to say this. Remember, the question is, what is the question? 5.3. So we'll say 5.3. We can say experiment 2 has higher concentration than in experiment 1. Or you can say experiment 1 has lower concentration than experiment 2. And we know that according to collision theory, the higher the concentration, more particles collide per unit time. More particles collide per unit time. Or since because we're talking volume, we can also say per unit volume, is still fine. Then now, what does this mean? It means more particles collide with enough, or we can say sufficient if we don't want to say enough, with sufficient kinetic energy, or even if we say energy, in brackets, we can say we are referring to where the average kinetic energy, it's either greater or equals to the activation energy. So more particles collide with enough or sufficient, not both. We can say enough or sufficient kinetic energy and correct orientation. So what does this mean? It means it will result to more effective collision, more number of effective. So more effective or number of effective collision. More effective collisions. More effective collisions per unit time. Hence, let us look at the question. Hence, higher or faster. Hence, higher reaction rate. Hence, higher reaction rate in experiment 2 than experiment 1. We can also do the opposite, ladies and gentlemen. So let me just go through this. Experiment 2 has higher concentration than experiment 1. It's true. And we know that the higher the concentration, more particles will collide per unit time. More particles collide per unit time. And if more particles are colliding per unit time, it implies that more particles will collide with enough or sufficient kinetic energy and correct orientation. And as a result, means the number of effective collision per unit time will increase or will be more. And if we have more effective or we have more number of effective collision per unit time, that means the reaction rate will be faster. So it's very important to talk about this. So it means in the context of maybe starting with experiment 1. If you say experiment 1 has lower concentration than experiment 2, it means we're going to say the lower the concentration, less particles collide per unit time, and less particles collide with enough sufficient kinetic energy and correct orientation. And as a result, it means less effective collision per unit time, then hence higher reaction rate in experiment 1 than, lower reaction rate in experiment 1 than experiment 2. Okay, I believe you guys are following. So we went through this one, we went through the first, second one, now we went through the third one. Now let us look at number 5.4. 5.4, it says the average rate of reaction in experiment 2. The average rate of reaction in experiment 2 is given as 4. The average rate of reaction in experiment 2 is 4.4 times 10 to the power minus 3 during the first 25 minutes. So what does this mean? I don't want to do it graphically already, but it just say that if we were to draw a graph, we'll say, okay, fine. We are now comparing the volume of gas that is produced and the time. Oh, but by the way, no. Let's look at what the unit or moles per minute. Moles per minute. So it means yes, not the volume, is the number of mole. It is moles per minute. So it means on the y-axis, we're actually given the number of mole, and in mole. So it means initially like something like this, as I just said earlier. So the graph looks like this, but there's no need to draw the graph. I just want to explain something. Maybe let's assume the time here, it's roughly 2.5, or in minutes, not in seconds. Right. Now, actually, during the first, which means from 0 up until 2.5. So it means we have to know this, then we look at the difference. So it means this is the final minus initial. Final minus initial. Okay? But now, by the way, it will not start at 0 because now, look, okay, it's fine. Let's just explain this, because it will not gonna start at 0, because if we're talking about what is this? Aluminium carbonate, its initial number of moles, it's provided. So it means I must not do this. Okay, let's just look at the calculation then. Okay, what are we given? We're given the rate of reaction. Okay, the rate of reaction is 4. Rate of reaction in experiment 2 during the first 2.5 minutes. Okay, let's write the rate of reaction. Okay, I want to change this in color. So in experiment 2, we are given the rate of reaction as 4.4 times 10 to the power 3 minus 3. Let's check the unit. It's mole per minute. Okay, what does this mean? Mole is the number of mole, is the n, then minute, it is the time. Okay, fine. So it means this rate of reaction is the changes in the number of mole over changes in time. Okay, during what? During the first 2.5 minutes, from time 0 to 2.5 minutes. So the question says, calculate the number of moles of aluminum carbonate that remains. Actually, want the number of moles that unreacted, that remain in the flask after 2.5. That remain in the flask after 2.5. But we want for aluminum carbonate. Right, we'll do this. We'll say, okay, fine. rate of reaction. According to this formula, it means it is the change in the number of mole over the change in time, where the number of mole is in mole, where the time it is in minutes. Right. What is the number of mole here? I'm saying the rate of reaction. It's 4.44. Let me confirm for the last time. 4.44 times 10 to the power minus 3. So we're going to say we have 4.44 times 10 to the power minus 3. The changes in the number of mole over change in time. Change in time is actually, remember they said during the first, so it means from 2.5 minus 0, which is just 2.5 minutes. Right, this over 1, so we can calculate the change in the number of mole. Right, then now, let us now calculate that. Okay, just a minute, guys. Okay, just give me 2 minutes, guys. I want to check. Okay, my apologies. I was still looking for my calculator. I apologize for that. So 4.4 times 10 to the power minus 3 multiplied by, so we want to multiply this by 2.5. This will give us 0.011 mole. Now we need to understand what does this mean by change? A change, it means it's a change from the final number of mole minus the initial number of mole, which is actually 0.011. Actually, this change, it is the number of mole of aluminum carbonate that has actually reacted. Why are we saying is the one that has reacted? Because we are actually comparing from the initial to the final. The final is when the reaction has come to a stop. So which means that not necessarily come, but it's just the unreacted. So if we take, we know that number of mole initial will be the number of mole that has reacted plus the number of mole that unreacted. So which means this change in the number of mole is the number of mole that actually reacted. So what is the initial of aluminum carbonate? So the initial number of mole of aluminum carbonate is given to be, from the reaction, is given to be 0. If I'm not mistaken, in experiment 2, it's 0. Let's check it. It's 0. Yes, 0.016. Yes, this is the initial number of mole of aluminum carbonate. So the initial number of mole of aluminum carbonate is 0.016. And from this 0.016, the reacted one, it is the 0.011 mole plus the number of mole that is unreacted. So which means that the number of mole that remained in the system, it will be 0.016 minus 0.011. And what is that? 0.016. Obviously, this will be 0.005 mole. I believe you guys are following. I strongly believe you are following, because this is the changes. It means we take the final number of mole, we minus the initial. So already it means the initial minus the unreacted will actually give us the unreacted minus the initial, but will be negative value. So it means we can either do it like this, or we use the other approach, but the answers will still be the same. But I believe you are following. So because if you want the number of mole that remained in the system, it means you're actually looking at the unreacted. The number of mole that remains, or the number of mole that were actually in excess. That's what you're looking for. And the reason I said we have to incorporate a minus is that, remember, if we say, I mean, if you don't want to use that approach, this is the one I explained now. If we say, remember, the N initial equals to the N reacted plus the N that unreacted. So you see that the unreacted will be the final, the reacted will be the initial. I'm saying the initial, like the initial will just be the initial. So how do you find, how do you do the changes in N? Remember, the changes in N is the number of mole final minus number of mole initial. And the final is the unreacted, the initial is, so you see that if we take this, we subtract, it means this thing has to be negative NR. So it means the reacted should be negative. So it means now, if we want to avoid this, we have to either put a minus here if we're doing the working. That will still give us the same answer here. I believe you're following. Right, let's move on. The second question says, calculate the maximum volume of carbon dioxide that can be prepared at 25 degrees Celsius in experiment 1. Take the molar gas volume at 25 degrees to be 24,000 centimeter cubic per mole. What do we want here? We want the maximum volume of the gas that is produced. But for experiment 1, this one, we want the maximum volume of the gas produced in experiment 1. Okay, let's do the working. So we want this volume of gas produced. But now look at this. If we want to know information about the gas produced, it means we need to consider the limiting reactant, because this one is in excess. It means we'll have to first get the number of mole of hydrochloric acid that reacted with that. So the best choice to use the limiting reactant, the information of the limiting reactant. So first of all, we'll say in experiment 1, we need to consider the limiting reactant because it will be used up. It's the one that will produce the carbon dioxide. Not necessarily that hydrochloric acid will not be used, to be used, but the reacted one. Since first, it means if we just go straight and we use hydrochloric acid, then it means we have to know the reacted number of mole, not the initial, because not all of it will be used up. So let's use the information of aluminum carbonate instead of hydrochloric acid. Because if you're using this, it means we must be able to know how many moles were reacted. And to do that means we're going to say, okay, fine. We have the information about aluminum carbonate. Aluminum carbonate. What do we have? We have the number of mole. Let me just write it here. We are given the number of mole of that. Is how much? 0. What is that? Okay, the number of mole of aluminum carbonate is 0.016. Because they said this is the limiting, it means it will be used up completely in the reaction, because they did not specify during what time. So it means we just assume that this has happened at the end of reaction. Okay, so it means to do that, we're going to say, okay, fine. Let us now use the information to actually calculate the mass, the maximum mass of carbon dioxide in experiment 1. So since we know the number of mole of aluminum carbonate, we'll use it to compare it with the carbon dioxide in terms of the reaction. So let us look at the aluminum carbonate from the reaction. We compare it with carbon dioxide, because remember, this will be used up completely. That's why I'm using it, unlike hydrochloric acid. So according to the mole ratio, 1 mole of aluminum carbonate will produce 3 mole of carbon dioxide. So it means we have 1:3. So I'm going to say 1:3. Now I have the information about aluminum. So it's 0.016. So I want to get this one. And to get this one means we're going to say 1 multiplied by x, it's x. So it will be 3 multiplied by 0.3 multiplied by 0.016. 0.016 multiplied by 3. It means the carbon dioxide will have the number of mole of 0.048. So which means now we have the information about carbon dioxide. Now we can use it to calculate the maximum mass. Okay, let's check what we're given. For carbon dioxide, we know the number of moles of carbon dioxide. What is the number of mole that were produced? 0.048 mole And since this one is a gas, it means we need to consider the molar gas volume is given to be 24,000 centimeter cubic per mole. And since we have number of mole and the molar gas volume, we can use this to determine the maximum volume of this gas that is being produced. Right, to do that, we'll say number of mole, we'll use the number of mole is volume over the molar gas volume. So number of mole, N equals to V over the molar gas volume, Vm. Okay. So this will be Vm. Right, number of mole, we know it's 0. We can just say volume, it's the number of mole over the molar gas. Let's do the substitution. The number of mole, it's 0.048. And what is the molar gas volume? The molar gas volume is 24,000. We just want to leave the answer in centimeter cubic. So it's 0.08 multiplied by 24,000. So this will be 1152 centimeter cubic. Because they did not say, it means even if we convert it to decimeter cubic, it means we have to divide by 1,000. Because they did not say anything, that means that is the answer. Stoichiometric calculations are very important. Okay, ladies and gentlemen, I believe you are following. So we have already answered all the questions here. We can now proceed with our workings. So if you're calculating the change, actually, usually you are calculating the number, the amount that is reacted actually. Okay, then now, let us now proceed with the second tutorial. In the second tutorial, it says, let us use reaction of sodium thiosulfate solution with dilute hydrochloric acid to investigate several factors that affect the rate of chemical reaction. The balance equation for the reaction is given below. Sodium thiosulfate is an aqueous solution. Even hydrochloric acid are both aqueous. So when we look at these reactants, it means the measures that might affect it might be, number one, it might be concentration. I mean, if we were to compare, because we are given aqueous solutions, we might add the catalyst, yes. I mean, if it's there, we might increase the temperature or decrease it. Temperature might be a factor. But pressure, it's not. It might not, because there is no gas here. Even surface area, it's not part, because surface area has to do with substances that are either solid or powder. So you see that the only factor that might affect this is either concentration or catalyst or temperature, but we'll check what we're actually investigating. Right, if you look at this, there's something that I said earlier about the color change in terms of precipitation. I said precipitation is a solid substance formed or produced in a chemical reaction. Formed in a chemical reaction. In the product, not the reactants. When you look at this is an aqueous solution. This is a gas. This is an example of a precipitate. So it means if we were to measure, we might use the volume of gas produced. might consider the issue of color change by looking at the precipitate. So you like, but it depends on the question. Okay, the first says define the term rate of refraction. I think I've explained that. Secondly, it says 3 investigation, 1, 2, and 3 are carried out. 3 investigation, 1, 2, and 3 are carried out. Right. Within this investigation, let us look on the first one. On the first one, it says it's investigation 1. It says within investigation 1, the result obtained in investigation 1 was shown in the graph below. So let's go through the graph. The graph on the y-axis speaks of the rate of reaction or reaction rate in mole per second. And on the x-axis is the concentration. We know that since this is the y and this is the x, so this is now a dependent variable. And this one is an independent variable. I think I've explained that. Okay, by looking at the graph, you can easily see that when concentration is, let's say it's 2 here, rate of reaction, so you see that when the concentration increases, even the rate of reaction becomes higher. So it shows that there's a direct proportion here. And I think I've said this, that when you're comparing rate of reaction, concentration and rate of reaction, they will be directly proportional. Okay, now let us go through the questions. It says, for this investigation, write down a dependent variable. This was just straightforward. Obviously, a dependent variable will be the reaction rate. So it means you're going to say independent variable will be the reaction rate. Conclusion that can be made by looking at this is an increasing line. It shows that there's a direct proportion between. So it means you're going to say an increase in concentration result to an increase in rate of reaction. You can even say the higher the concentration, the faster the rate of friction, or there's a direct proportion between the two. Okay? Now, let us continue. Investigation 2. The Maxwell-Boltzmann distribution curve A and B below represent the number of particles, on the y-axis, and the kinetic energy on the x-axis. I think I spoke about this. For the reaction at 2 different temperatures, Right, you are told that this shaded region is a particle that undergo effective collision. So it means is the area where, the P here, the P is our activation energy, as I said. So it means this is the area where the kinetic energy is greater or equals to the EA. So it means particles are with sufficient kinetic energy. Okay, then now, what does the line P represent? Obviously, I think I've explained that it is an activation energy. The energy that is needed for the chemical reaction to start. Which curve between A or B was obtained at higher temperature? Remember I said, look at the area. Curve A has a very small area as compared to B. Let me use a different color. So if you look at the area behind, you see B include almost everything. Then the other part for A, is it B? Yes, B. Then for A, it means it's just this part only. So you see that it means B, more particles have sufficient kinetic energy, or more particles undergoes effective collision than that of A, if I'm not mistaken, the A, yes. So what is the answer here? The answer is B. B is obtained at higher temperature. B is this one. It says, in terms of collision theory, how an increase in temperature will influence the rate of friction. It's like we're just going to talk about what I said. Then we're going to say an increase in temperature. An increase in temperature. We can just write it in one place. More particles collide per unit time. And these more particles will collide with sufficient more particles collide with enough kinetic energy. In brackets, we can say where EK is greater or equals to the EA, and correct orientation. Then still we are not done. If we have that, then it means more effective collisions per unit time. Hence, faster reaction rate. But what is actually important is to talk about the number of particles that are colliding per unit time, the effective collisions per unit time, and also the issue of enough kinetic energy. Okay? I believe you guys are following. The higher the area, in terms of the area, look where the kinetic energy is above. Remember, this is where the EK is great. I think I've said that. So it means this side, the EK is less than the activation energy. Okay? I believe you're following. Remember, practice makes perfect. Right, let us move on to the next question. Okay. 5.4, it's experiment 3. The potential energy graph between X and Y below represent the reaction under two different conditions. Actually, this potential energy falls under chemical change. We will talk about this. I think I will create a video. This is the reactants and this is the product. And we know that if we have more, more reactants, energy of the reactant it's higher than energy. So this is an example of an endothermic reaction. It is an example of an exothermic reaction. But we're not concerned about that because products are less than the reactants. But when we look at the two potential energy, we have potential energy for X and potential energy for Y. And when we look at this, we can try to analyze this to say, we know that from the reactant to the highest point of the potential energy, which is called an activated complex. It's actually called an activation energy. So it means from X up until the reactance, this is our EA, especially for forward. Same applies with this one is the E activation. So you see that the activation energy for Y, it's smaller than that of X. What could be the possible reason here? The addition of a catalyst. Catalyst speed up the reaction by lowering an activation energy and without undergoing any permanent change. What does it mean? Without changing the reactants or the product. It's just speed up the reaction, but without changing the reactants or product. So give a reason why curve Y differ from curve B, curve X. Obvious, curve Y, it is the curve that is having a catalyst added, with catalyst added on it. So the Y, it is that without a catalyst. Curve without a catalyst. Okay? Then now let's move on. In one of the investigations, they did not mention which one. In one of the investigation, 100 centimeter cubic of 0.2 mole decimeter cubic react with excess, very important, excess sodium thiosulfate, and the solution is then filtered. After filtration of the solution, only 0.18 grams of sulfides obtained. So it means this is the actual mass. The actual mass of sulfur is given by 0.18 grams. So the question says, calculate the percentage yield of sulfur. Obvious, when we want to calculate the percentage yield of sulfur, okay, let me just write it here. Right, to do the calculation, let's first copy the equation, because I want us to have this equation here. So that, because that we're talking about the two reactants, okay? Let me copy the balance chemical reaction so that we're able to use it. Yeah. Okay. That's fine. It's not working. That's okay. Okay, we'll just go back to our working. Just close it. Right, we are told that 100 centimeter cubic of 0.2 of hydrochloric acid react with sodium thiosulfate. Now, what we're going to do is, let me just take this information back to that one, okay? What is this? 100 centimeter cubic with concentration of hydrochloric acid, okay? Let me write it here. So it means this one has it's hydrochloric acid. This one has a volume of 100 and concentration of 0.2. But we are told that this is in excess. And what do we want to calculate? We want to calculate the percentage purity of sulfur. Okay, I'm sorry, percentage yield. To calculate the percentage yield, what do we have to do? We have to take the actual mass of the substance. We divide by the theoretical one. And we multiply by 100. Already the actual mass we are given, because they told that after filtration, they obtain a mass of sulfur to be 0.18 grams. So already we have the actual, so we have to get the theoretical from the reaction. Now look at these guys. We're given the information for hydrochloric acid, and they told us that this was an X, which means we're not going to use sodium thiosulfate. Why? Because if we use the information of sodium thiosulfate, it means not all of its mole will react, some will remain. So it means you have to use this one because this one is the limiting. So we're going to say, okay, fine. We have the information for hydrochloric acid. We know the volume. The volume is 100. We're going to divide that by 1,000, which will be 0.1 decimeter cubic. Concentration we know is 0.2. Then we're going to say concentration is the number of mole over volume. Then we make N the subject. So it's N equals to CV. The C is 0.2. The volume is given as 0.1. Let's now calculate the number of mole. So we're going to have 0.2 multiplied by 0.1. So this will give us a mole of 0.02 mole. So this is the number of mole of HCl. But now we do not want to know about HCl, we want to know about sulfur. Now we're going to use stoichiometric calculation to say we are comparing hydrochloric acid and sulfur. Why not using sodium thiosulfate? Because it is in excess. It means this will be the reactant. So in terms of mole ratio, it shows that 2 mole of hydrochloric acid will produce 1. So it's 2:1. So what is the number of mole of hydrochloric acid? 0.02. So this is X, then we cross multiply. This is 2X equals 0.02. So we divide by 2, this will be 0.01. So it means that the thiosulfate has about the sulfur, sulfur has the following information. We got the number of mole to be 0.01, and we want the mass. So we're going to say, what is the molar mass of sulfur? The molar mass of sulfur, if I'm not mistaken, sulfur has a molar mass of 32. I don't have the periodic table with me. Okay, just a minute, guys. I think it should be 32, if I'm not mistaken. Sulfur, yes, it's 32.1, which is just 32 grams per mole. Now we will calculate the mass. It will be number of mole is the mass over the molar mass. The molar mass, the bigger M, okay? Then let's do the substitution, ladies and gentlemen. I believe I'm not confusing you. So, okay, let's just do it here. Okay, let's just do it somewhere here. So let me just take this. Right now about sulfur, number of mole, it's 0.01. Molar mass of sulfur, it's 32 grams per mole. So number of mole is mass over the molar mass, that's over 1. Cross multiply, then the mass will be Nm, and what is the number of mole? 0.01 multiplied by 32. So 0.01 multiplied by 32, this will give us the number of mole of 0.32. I'm sorry, the mass. So it means this is actually the theoretical mass or the calculated mass. So to come here, we're gonna say, okay, fine. Now we know the theoretical mass and the actual mass after filtration. So we're gonna use this and say, what is the actual? Actual is 0.18. Theoretical is 0.32. Then we multiply that by 100%. So 0.18 divided by 0.32. Multiply that by 100. This will give us 56.25%. 56.25%. So in most of the time, guys, if you want to determine the components of the product, when you are told that one substance is in excess, you need to use the one that is the limiting. Unless if you can be able to get the reacted number of mole of that substance that is in excess. I believe you are following. I believe you are following. So we have percentage yield, and there's also what is called percentage purity. Where we take mass of a pure substance we divide by the mass of the impure substance. This percentage purity. And guys, it's very important to be able to know that once they say one substance is in excess, it means the one that is reacting with is the limiting. It will be used up completely in a chemical reaction. Used up completely in a chemical reaction. So I think this is the end of the session, ladies and gentlemen. Kindly don't forget to like, subscribe, and hit the bell notification. That will be much appreciated. Okay, let me check before I close. Okay, Maxwell Boltzmann distribution curve. Yes, that is the end of the session. Remember, practice makes perfect. So you need to be able to use collision theory in explaining the factors that affect the rate of reaction. And either you talk about temperature or pressure, even pressure in some instances, even surface area. Surface area, as I said, you look where substance has been converted from solid to liquid. So practice makes perfect, ladies and gentlemen. Okay, let me go back to... Guys are following, guys. Yeah, I think this is the... I wanted to check something. Okay. Yeah, okay. Anyway, goodbye. Take care. Thank you very much.